In lesson 5, we're going to continue talking about increasing and decreasing functions, but like with everything we've been doing, we're going to kind of add a little bit more to it. The last lesson, we focused more on linear equations. We're still going to do that this lesson, but we're going to also start working on some nonlinear equations. So let's just kind of look at a couple examples. Remember, with everything we're doing is we're basically trying to read graphs and make sense of them. Okay, so it says not all real-world situations can be modeled by a linear function. Truth. So we're describing nonlinear or linear functions describe a relationship between two quantities. So remember what I always said, you pay attention to our labels here. So ELF is running at a constant rate. Notice it doesn't say that one quantity is constant. We're saying that the rate is constant. Constant rate means linear. And it's a flat paved road. And the graph represents the total distance he covers with respect to time. So again, we have our time in minutes and we have our total distance in miles. Okay, so what is this graph telling us? Well, it says, in your own words, describe what happens as alpha is running during the following intervals of time. Well, 0 to 15 minutes. So what we can do, 0 to 15 goes from right here to right here. This is 15, right? So if we look at 15 minutes, because the x-axis is minutes, it looks like he is running 2 miles. So we can say, oh, I am struggling today with writing, so we're just going to go this way. Alf runs 2 miles in 15 minutes. Okay. So then it wants from 15 to 30 minutes. Okay, so now what we're going to do is we're going to go from 15 to 30. Okay, so from here to here, he is running how much time compared to how much distance? Well, if we're going from, from here at 15 to here at 30, he's running 15 minutes. If we're going from 2 right here to 4, he's running 2 miles. So we can say 2 miles and 15 minutes, which is 4 total miles and 30 total minutes. Right? Because if we just look from 0 to here, that's what's happening. Okay? But we only want the section from 15 to 30. Okay? And then I guess we'll look at our last one here. We are going from 30 to 45. Okay? And so if I'm going from 30 to 45, looks like I'm going over 6. Now again, when we're talking about our intervals here, this is 45 right here, right? So if I'm going 30 to 45, that's 15 minutes. And then I was right here at 4 miles, and now I'm at 6 miles. So really, it's going to be the same type thing. 2 miles in 15 minutes. And this time, it's 6 total miles and 45 total minutes. Okay? But what we notice in each of these, 2 miles, 15 minutes, 2 miles, 15 minutes, 2 miles, 15 minutes, constant rate. Now let's compare that to Shannon. Now Shannon's running on a flat, rocky trail that eventually rises up a steep mountain. Okay, so the graph below shows the total distance with respect to time. So again, we have time, and here we have total distance in miles. And we can see that this is not a linear function. Okay, so it wants to know what is happening from 0 to 15. Okay. Well, from 0 to 15, it looks like she is going to cover 3 miles, right? So we can say Shannon runs, I'm sorry, that's not 3. You probably are catching that, right? Man, I was doing so good. Not messing up too bad. 1 to 2. Duh. This is 1.5. Sorry. There's my first of many mistakes, right? So what we can say is that she runs 1.5 miles in 15 minutes. Okay, but now, like we did with Alf there, now we want to go from 15 minutes to 30. Okay, so if I look at the graph, we're going up just above the 2, not to 2.5 yet. So, but remember, we're going from 1.5 to, I don't know, maybe 2.1. 2.1. Sorry, that's hard to see there. Okay, so if we're still going the 15 minutes, but notice if we go from 1.5 to about 2.1, we're only going up about 0.6, 0.6 miles in 15 minutes. And that's not exact. We can't tell exact, but best guess. Okay, now in this case, we can say that we've traveled a total of 2.1 miles. That's where we're at. Total in 30 total minutes. Okay. All right, and then finally, of course, we want to go and take our next block here from 30 minutes to 45. All right, so if I look at that again, it looks like I'm going to be, I don't know, again, just up the past 2.5 here, right? So maybe we would say 2.6. Above that line there. That's better. Okay. So I'm going to say maybe 2.6 because it's right past the 0.5. Remember, we're going up by 0.5. So that's where I messed up earlier. So, okay, if we're going from 2.1 to 2.6, that's only 0.5 miles in 15 minutes, or a total of 2.6 miles, total miles, in 45 total minutes. Okay, so what do we notice with that? With Alf here, I could underline 2 miles, 15 minutes, 2 miles, 15 minutes, 2 miles, 15 minutes, because that was a constant. But here, I can't. We went 1.5 miles in 15 minutes, but then we went 0.6 miles in 15 minutes, and then we went 0.5 miles in 15 minutes. So time is still going by. The line is still increasing, but it's not increasing at the same rate. Okay, and that's the kind of stuff we're going to be working on today. So it says the rate of change of a function can provide useful information about the relationship between two quantities. Guys, the quantities are x-axis and our y-axis. Time in minutes compared to total distance in miles. A linear function has a constant rate of change. 2 miles, 15 minutes, 2 miles, 15 minutes. A nonlinear function has a variable rate of change. And this word variable here means it varies. Okay, it's not increasing by the same number every single time. Okay, so if you kind of look at this chart right here, it gives you some examples, right? So a linear function increasing at a constant rate, we see a nice straight line. A nonlinear function also increasing, but this time at a variable rate. You can see that as time goes by, we read our graphs from left to right, the graph is increasing, but it's not straight. So that means that rate of change is going to be changing. It's not going to be the same every time. It varies. So in the next one, if we have a linear function that's decreasing at a constant rate, it's a straight line going down. It's dropping at the same rate. But a nonlinear function decreasing at a variable rate, it's still going to go down as time goes by, but not by the same amount every single time interval. When we have tables, okay, a linear function with a constant rate means, again, we're increasing every single time, okay? So if I start my first point here at 0 to 7, and I notice I'm going up 1 every single time, so 1, 2, 3, 4, then over here, notice I'm also increasing at the same rate. 7 to 10 is plus 3, 10 to 13 is plus 3, 3 to 16 is plus 3, and you guessed it, 16 to 19 is plus 3. But a nonlinear function with a variable rate, we're still going up 0, 1, 2, 3, 4. We're increasing by 1 unit every time. But if I go from 0 to 2, I go up 2. If I go from 2 to 4, I go up 2. But if I go 4 to 8, I go up 4. And 8 to 16, I'm going up 8. Okay? Nothing wrong with that. Notice they're still functions. The difference, okay, is linear functions have a constant rate. That's why they're a straight line. Nonlinear functions don't have that constant rate. They have a variable rate, which is why their graphs are not straight lines.